Hello friends, welcome back again. In this section, we will talk about some previous year gate questions on fluid kinematics. So till now we have studied about the fluid kinematics part, and we have seen what are the various things that comes under the fluid kinematics when we talk about the fluid flows without considering the forces due to which the flow has been occurred. So now moving on, in this section, the previous year gate questions we will discuss. So in this topic, we will cover some questions from types of flows, streamline, path line, streak lines, flow acceleration, vorticity and circulation, stream function and potential function. So these are the topics that covered in fluid kinematics part. So now moving on. In GATE 2018, question is asked for 1 marks. It states a flat plate of width length 1 meter. Here the length is 1 meter is pushed down with the velocity 0.01 meter per second. So this is the velocity by which it is pushing down 0.01 meter per second towards a wall, resulting in the drainage of fluid between the plate. Here the fluid is filled between the plate. When we push down this plate downward, the fluid will go along the plate outside with some velocity. We take say average velocity as u average. So assume two-dimensional incompressible flow. The incompressible flow is mentioned here, and that the plate remains parallel to the wall. So this plate will remains parallel and just moving downward, and in this position, the average velocity is u average of the fluid draining out at that instant. So we have to find out the velocity of the draining out fluid at a particular instant. So we have to find at this particular instant when the depth difference, the gap between the plates is 0.1 meter, what will be the velocity of fluid that is draining out from between the plates. So here first of all we will use the continuity equation. Continuity equation is, we have talked about the continuity equation, that amount of fluid which is coming into a volume, if it is a steady flow, that much amount, say m1 mass of fluid is coming into the volume and m2 coming out from the volume. So the continuity equation states when the flow is steady, m1, the rate at which the mass is moving in a control volume, will be coming out at the same rate from the control volume. So here let's say by conservation of mass, we can say if at this portion the mass that the upper plate displaces downward, that much mass will be coming outward from both the direction. Okay, the mass that the upper plate that pushing downward, that much amount of mass will be coming out from both the direction. So here we can write the amount of fluid that is coming out from the drainage part. We can write twice of mass. We can write mass as density u average into the area, and area will be, let's take the width here, let's say the width in between into the plane as b, and d is the depth, So if we make a cross section here, let's say it is a cross section, the b which is into the paper and a depth d between the plates, and it is moving with velocity u average. So that much amount of volume will be coming out here. The same amount which is moving from the left hand side will be the same amount will also move from the right hand side. So that's why we multiply it 2, this will equal to the mass that is displaced by the top plate. So here we can write mass. How can we write? Density into volume. So density into the velocity by which this plate is moving downward, which is u, into the surface area of the plate. So we have taken the width of the plate of the both plate as b. So multiplying as b into, and this length into L. So by putting the equation, by putting the values, we can have twice of density is cancelled out from both the side, and as well as B, the width is cancelled out from both the side. We will have twice of A average into D. D is given 0.1 meter, and U is also given 0.01 meter per second, into L. L is the length of the top plate, which is 1 meter. So here we can find the velocity, average velocity will be, comes out to be 0.05 meter per second. So it is a very simple question which is asked for 1 marks in GATE 2018. We just have to take the conservation of mass. Okay, so we will get the answer as 0.05 meter. So now moving on, another question is asked from the GATE 2018. This question is for 2 marks. In Lagrangian system, the position of fluid particle in a flow is described. The position, here please note it down, the position is given, x and y coordinates is given of a fluid particle in a fluid flow, where t is the time. This position, the position of fluid particle is dependent on time, because in this here time is mentioned. The location, the position, time is mentioned, while the x naught and y naught and k are the constant. These are the constant. The flow is asking what will be the flow. So first of all, for this it is given, say x, it is given x is equal to x naught e to power minus kt, and y is equal to y naught e to power kt. So these are the location, these are the position of the particle. So we know that if we differentiate with respect to t, the location of this particle, it will comes out not equal to 0, because it is dependent on temperature. So derivative will comes out some value, some finite value. Similarly, dy by dt is also not comes out to be 0. So here we can say the location is changing with respect to time. The location is changing with respect to time, but here it is asking about the flow. Here it is asking about the flow. So we have to find out the velocity. So velocity, how can we find out? Dx by, we can find out dx by dt. It is equal to u. It is x is the location position vector. We take a derivative with respect to time. We will get a velocity in the direction of x axis, which is equal to u. So what will we get? X naught minus k into e to power minus kt. Okay. Here we can write, taking minus k outside. So we can say minus k x naught e to power minus kt. So this is the value we have given already, which is equal to x. Okay. Similarly, dy by dt, we will get the velocity in y direction. We will differentiate it. We will get x naught k e to power kt. So here taking k outside, and the remaining part will be equal to y. Okay, from this we can say the velocity is in velocity equation. These are the velocity equation. In velocity equation, there is no time term is coming out. So here we can say these velocity as independent of time. Here only the position, here the position x and y is coming in the equation. So here we can say these are the steady, because in the flow equation there is no time terms coming in the equation. So we can say it is a steady, and the u and v have the different velocities in x and y direction. So we can say it is a steady and two-dimensional flow, because the velocity is varying in x and as well as in y direction. So the answer should be velocity steady and two-dimensional flow. So this is how the question is asking. Here it is 2 marks question, because the student can be confused in x and y. So x and y is the location, is the position coordinate. We are asking in the question, it is asking about the flow. So we have to find out the velocity field. Okay, but velocity field is coming out to be independent of temperature, or time. So it is a steady flow. Now moving on, the another question is asking in 2017. It states, consider the two-dimensional flow. Two-dimensional flow is given velocity field, it is the velocity field of two-dimensional flow, and A1, B1, A2, B2 are constant. So which of the following condition needs to be satisfied for an incompressible flow? So this type of question generally asked in the examination. Many times they are question asked in the examination from the incompressible flows. So we know that incompressible flow, what is the equation of incompressible flow? It is the equation in incompressible flow, divergence of velocity equal to 0. So I had told you earlier in the previous videos how to find the equation of incompressible flow. So this is the equation in incompressible flow. Please remember this equation. Okay. So what we have to find out, we just have to find the divergence of the velocity field. So how can we find out? Del u by del x plus del v by del y is equal to 0. So here it is u and it is v. So we can have to find the derivative of partial derivative of u with respect to x and partial derivative of v with respect to y. We will get, if we derivative it with respect to x, we will get this term will be cancelled out, this term will be cancelled out, only a1 will be get. a1 plus, and here with respect to y, these two terms will be cancelled out, only b2 will be there, which is equal to 0. So directly, simple, just putting the equation, incompressible flow equation, we will get the solution. So answer is B, A1 plus B2 equal to 0. It is very simple question, and this question generally asked in the examination. Again, moving on, in 2015, for 1 mark question is asked, it states if the fluid velocity of a potential flow is given. Again, fluid velocity potential flow is given with usual notation, u and v is the velocity in xy direction, v is the velocity component in y direction. Then the slope of the potential line. It is asking about the slope of the potential line. So slope of the potential line, we know, we already find it out how to find the slope of a potential line. So let's say phi is a potential function. Let's say phi potential function defined by the phi. So phi is a potential function which is constant and which is a scalar function of x and y. So we can say phi is equal to, we can take the derivative, how to find d phi will be equal to del phi by del x into dx plus del phi by del y into dy. This is how we find the derivative of a function. So but we are stating that we have to find the equation of a equipotential line, that is potential line having the same potential at every point. So d phi will be equal to 0 because the potential is not changing. So this equation will be equal to 0. Here del phi by del x, again del phi by del x is the, we know that how to find, if we take the negative derivative of del phi by del x, it will give u component. If we take the negative derivative of del phi by del y, it will give y component. So putting just here, we will get minus u dx plus minus v into dy equal to 0. So slope is nothing, slope is nothing, it is dy by dx. Taking dy by dx here, we can get u by v minus u by v. So this is how we find the equation of a potential line. So the slope of a potential line is minus u by v. So option B is correct. Now moving on, in 2014, for 2 marks question, it is asking, consider the following statement regarding the streamline. Okay, regarding the streamlines, it is a continuous line such that the tangent at any point on this line shows the velocity vector at that point. It is right, it is exactly correct. It is a streamline. Any tangent at any point gives the direction of velocity of a point at that location. Okay, so option 1 is correct. There is no flow across the streamline. Exactly, there is no flow across the streamline. I told you how, why don't there is no flow across the streamline. Okay, so option B is also correct. Del x by del x by u is equal to del y by v, sorry, dx by u equal to dy by v equal to dz by, so we already studied about earlier, it is the equation of a streamline, differential form of equation in streamline. So it is given, it is the differential equation of a streamline where u, v, w are the velocity in x, y and z direction. Exactly, it is correct, totally correct. In an unsteady flow, the depth of a particle is a streamline. No, it is not correct. Streamline is defined for when a streamline or the stream function is given, the flow should be steady, incompressible. Okay, so option D is correct. So the correct answer is A, 1, 2 and 3. So option D is right answer, right, correct answer. Okay, so another question is asking here for 2 marks. It states you are asked to evaluate the assorted fluid flow for their suitability in the given laboratory application. Okay, here the 3 conditions are given. Flow field is given, u and uv in x and y direction velocity fields. The following 3 choices expressed in terms of 2-dimensional velocity field in xy plane are made available. Which flow should be recommended when the application required to flow to be incompressible and irrotation? So here we have to check which one have the both conditions satisfied, incompressible and irrotation. So here for this we have to find one by one. Let's check for the incompressible flow. Let's check for P. For incompressible flow, we know that del dot V should be equal to 0. Divergence of velocity should be equal to 0. So here taking del u by del x plus del v by del y equal to 0. It should be 0. So let's check, is it coming out to be 0? So here del u by del x, it will be 0 because no x component is here. Del v by del y, it is also 0 because no y component is here. So it comes out to be 0. It is incompressible. But we have to check whether it is irrotational also or not. So how to check rotationality? The rotation is given, that is curl of velocity. If we have to find the rotation about z axis, how can we write? Del v by del x minus del u by del y. So just try to find out, is it coming out to be 0? So just put del v by del x. Del v by del x comes out to be minus 3 minus del u by del y comes out to be minus 2. No, it is not coming out to be 0. So it is not a irrotational flow. So option 1 is correct. So similarly, we have to find both condition in which option is satisfying. So by solving the same procedure, by following the same procedure, we will get the number R, u is equal to 2 minus 2x and v is equal to 2y will satisfy both the condition. So option R should be correct. So just try yourself, try to find out whether Q or R is coming out to be incompressible or rotational. So you will get R as incompressible and irrotational flow. So the question is asking in 2008 for 1 marks for a continuity equation given by, this is the equation given to be valid where V is the velocity vector. Which of the following is a necessary condition? Sorry. So we know that the continuity equation is given by d rho by dt plus del dot rho times V. It is the continuity equation. We have talked earlier in the previous videos. This is the generalized continuity equation. So we have to check what condition should give this equation. Okay, now first check for the steady condition. If we have the steady condition means the properties of flow doesn't vary with time. So this particular term comes out to be 0. So what will we have? Del dot rho equal to 0. This is the divergence of rho into V. Here density is varying, density isn't varying with respect of time, but it may be varying at a location to another location. So here del dot rho V is equal to 0. So no, we are not getting this equation. So it is not for only for the steady flow. And talking about the irrotational flow, and it is not for irrotational flow. Okay, inviscid flow is not coming in the continuity equation. Let's check for the incompressible flow. Again, taking the equation d rho by dt plus del dot rho v equal to 0. This is the continuity equation. If density is invariable, incompressible flow means density is not varying with space or time. So density is not varying with the space of time. So this term will be 0 because it is invariant with time, and again it is invariant with the space. So we can take out this term outside. So it will be del dot v equal to 0. So density is not obviously 0. So this term should be 0. So this is the equation of continuity when we talk about the incompressible flow. So option D is correct. So let's just take another question. A 2D flow with velocity field. A velocity field is given u and v. It is u and v is given. So what is the equation? We have to check it is compressible or irrotational. So we have to find out if it will satisfy del dot v is equal to 0, it is incompressible flow. If it will satisfy omega about z equal to 0, it is irrotational flow. So let's check out first. Del u by del x, del v by del y equal to 0. So let's check del u by del x. Del u by del x will be 1 plus del v by del y comes out to be minus 1 equal to 0. Yes, it is incompressible flow. Now check for the rotationality. Del v by del x minus del u by del y. So we can write del v by del x, it is v. So del v by del x is equal to 0 because there is no x component, and del u by del y is equal to, it will comes out to be 2. So it is not equal to 0. So we can say it is a velocity field which is incompressible but not irrotational. So option B is correct, incompressible and not irrotational, because it is not coming out to be 0. So this is how we solve the equation fluid kinematics. This is the level on which the question will ask. No such a high level question will be asked in the GATE examination, and basically these are the topics from which the questions generally asked in the examination. It is very important to note down from the continuity equation and from the incompressible flows, the questions generally asked in the GATE examination. How to find out the rotationality, how to find the flow maybe is irrotational or not. So it is very important. So just keep some focus on these topics. So now this is all about the fluid kinematics part. In the next video we will start about the fluid dynamics. Okay, we will talk about fluid dynamics. So thank you so much.